My name is Molly Johnson, and this is my video for Lab 4, the Circuit Lab. Purpose. So the purpose of this lab was to model circuits online using the Circuit Construction Kit. We were to create short circuits with resistors, power sources, ammeters, capacitors, etc. We were to take data measures and compare calculated results to equation-based results. And during this lab, we had to calculate the current I and electric potential V at various points. The final part of this lab was to graph the natural log of the electric potential over the initial electric potential to find the time constant RC. Key concepts of this lab was Ohm's law, V equals IR, the loop rule that V of a closed circuit is equal to 0, the resistance of a series rule, the resistance in parallel rule, that V capacitor was equal to Q over C, and the electric potential versus time equation. Calculating I. So the first part of this lab, we had to create this circuit, seen on the left, in the CCK, which is shown on the right. To calculate I used Ohm's law, the resistors in a series rule, and the loop rule to get V equals IR. And then solving for that, I was equal to 0.0204 amps. And as you can see, the ammeter did read the same output as my calculated value. The next part of this lab was determining whether reversing the ammeter would change anything. And as you can see, the output is the same, so there's no change. For the next part of the lab, we had to use the voltmeter to measure the electric potential of the circuit. And as you can see in the reading, it was equal to 3 volts. This makes sense since we used two 1.5 volt batteries, so 2 times 1.5 is equal to 3. And the ammeter reads 0 at this point because the circuit is open, so there is no current flowing. For this part of the lab, we had to calculate the electric potential around the circuit. As you can see, over all of the wires and over the ammeter, the electric potential was equal to 0. Over the battery, the electric potential was equal to negative 3V. Over the 47 ohm resistor, the electric potential was 0.959 volts, and over the 100 ohm resistor, the electric potential was 2.041 volts. The predicted value, according to the loop rule, would be that V total is equal to 0, and the actual value was indeed 0. The voltmeter is connected in parallel, so the ammeter reading does not change when taking the electric potential measurements around the circuit. For this part of the lab, I had to graph the potential versus the position. So as you can see, over all of the wires, the slope is 0 because there was 0 change in potential. Over the battery, there was a change. Over the resistors, there was a negative change. And that the initial and end, you start with 0 volts and you end with 0 volts. The ammeter in parallel. Placing the ammeter in parallel with a resistor alters the current. Instead of using the R series rule, we had to use the R parallel rule. So this changes the V equals IR equation so that I equals 0.0638 amps. And as you can see, the reading does change. Resistance calculations. So using Ohm's law, we could calculate the resistance for each of the pieces of the current of the circuit. So the resistance for the 47 ohm resistor was indeed 47 ohms. Same for the 100 ohm resistor, it was 100 ohms. And for the wire and ammeter, the resistance was equal to 0 ohms each. For the RC circuit, the first circuit, we used a battery plus a 10 ohm light bulb plus a capacitor. Over time, the bright light went out, the current stopped, and the capacitor charged. For the second circuit, it was just the 10 ohm light bulb plus the capacitor. And over time, the light went out, the current stopped, and the capacitor discharged. We also repeated this process for a 20 ohm bulb. So for my measurements for the 10 ohm light bulb, the average charge time was 40.92 seconds and the average discharge time was 23.31 seconds. For the 20 ohm light bulb, the average charge time was 80.2 seconds and the average discharge time was 46.11 seconds. For the last part of the lab, I plotted the natural log of the electric potential over the initial electric potential and set that equal to negative t over the time constant. As you can see, my original values are in the red box and then the converted values are in the green box. The converted values were then plotted, and judging from the line, RC, or the time constant was equal to negative 1 over the slope, so RC was equal to 0.109, and RC is the time at which the electric potential is equal to the initial electric potential divided by E. The initial potential divided by E was equal to 3.331 volts, but as you can see at time 0.109, the voltage was not 3.31, so for my data, my time constant was not accurate. What if? So if we were doing this lab in real life and used an actual ammeter instead of a simulated ammeter, the real ammeter would have had some resistance, whether it be almost negligible or not negligible, and it would have altered the current and then therefore the measured electric potential. And if we were doing this lab in real life and used a real battery to charge a real capacitor with no resistor in the circuit, the capacitor would have charged much faster without the resistor, and it would have been almost instantaneous, but not quite because of real life constraints. And that's the end of my video. Thank you for watching.